Unit 4 is on the graph of f prime and f double prime and how it relates to the graph of f. Actually switched up the order of units from last year. I feel like this is the right unit to do at this time. We will move into what is considered a harder unit next unit instead of right now, which is good. Okay? So this is applications of derivatives. So we're going to be doing derivatives, finding derivatives, and using derivatives to help us understand what our function looks like, how it reacts, where it has certain particular points of interest that we're going to kind of focus on. And the first kind of point of interest is a critical point of a function. A critical point of a function is when the derivative of the function equals 0 or when it's undefined. Okay? Now let's look at a graph. This is a graph of f. I'll start marking off some critical points. Now we know when the derivative is equal to 0, that means we have a horizontal tangent, right? So I got a horizontal tangent here, 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 here. I also have a derivative that is undefined here. These are all 0 slopes. So what is occurring at these locations? That's maybe interesting. Yeah, it's a critical point. But why is this critical point of this function interesting? The derivative of f of x at those locations are 0 or undefined. Yes. That's what we are defining as a critical point. Why there? Why not look at when the derivative is equal to 1?
Because when the derivative of that graph can be factored into different polynomials where they will equal 0 at this point.
Yeah, kind of, but like just look at the graph. That's a good thing. I like that. This is a point where maybe the slopes go from positive to negative. This is a point where the slopes go from negative to positive, positive, negative, negative to positive, positive, negative. Well, that's also a location where we have maximums and minimums, local maximums and minimums. Of our function. Wherever we have a little hump, where we kind of have an extreme value, that's a local max or a local min. So right here, we can consider this a local max. This point down here, where my derivative is undefined, that's a local min. Right here, local max. This would be a min. This is a max. And exactly what Ms. El Haji said, I like it. Our derivatives are changing sign at the location. A very good observation. Okay? So, critical points are where local maxes and mins occur of my function. Okay, so whenever I have a derivative equal to 0, or it's undefined, I'll have a little hump, maybe. Or I'll have a sharp point, maybe. Is there any one that I missed, though? Mr. Lusu, did I miss something? Yeah, right here, I missed this derivative. This derivative is also 0. Now, maybe this is not a good example. Maybe I can zoom in and it looks like this. This is a point where the slope is horizontal. The slope of the tangent is horizontal. Is that the location of a max or a min? No. It's neither a max nor a min. It's an interesting point, sure, but that just changes this definition. Instead of where all of our local maxes and mins occur, it's where our local maxes and mins could occur. So all maxes and mins will occur at a critical point when the derivative is equal to 0 or when it's undefined, but not every critical point is a max or a min. Okay, we've kind of been doing this. We've been finding horizontal tangents already. These problems that we're going to be doing this unit really aren't going to be dissimilar from the problems we've already done. We're just going to focus on them a lot more. Okay, we will be finding specifically these points for all these different types of functions, and we're going to be analyzing them. Okay, so maybe we didn't know why we were finding horizontal tangents, but now we know. We're finding locations of horizontal tangents or tangents that are undefined because they're these interesting points of my graph. They're these maximums or minimums. There's another mathematical way that we can call these maxes and mins. They're called extrema, and you need to know this term, extrema. You can think of like extreme function values. There are two different types of extrema. We're going to focus on one type this unit and another type in another unit. First is relative extrema. Which are the local maxes and mins we're talking about. And then there are absolute extrema. Which would be overall maxes and mins. For this unit, we'll focus on relative extrema. We will look at graphs and see where do we have a local max or a local min. Now, take this graph. These are local maxes and mins. However, looks like these two locations right here and right here, those seem to be at the same y coordinate. Those also could be considered absolute maxes of my function. Now, what about this down here? Would this be considered the absolute min of my function? No, because my function goes down onto the sides. There actually isn't an absolute min. Okay? We're not going to worry about that so much. We're just going to worry that it's a local min. We're going to worry that this is a local max for now. Okay? Sweet. Well, let's start finding critical numbers given a function. So instead of giving you a graph, I'll give you an equation, and I will ask you to find the critical numbers. You've done this before many, many, many times. This is just another type of way of asking, when does the derivative equal 0? Or when do we have a horizontal tangent? And we also have to consider ourselves not necessarily with just horizontal tangents. We also have to worry about vertical tangents, or tangents that occur at sharp points. So I'll do this one, you'll do this one. Simple. Try to find the critical numbers of this. Take the derivative. Set it equal to 0. And consider if it's ever going to be undefined. I know 12x cubed minus 12x squared is a polynomial function defined everywhere. So I'm not going to worry about this piece because it'll never happen. I'll just worry about when this is equal to 0. I will factor what I can out of both terms to solve. At x equals 0 and x equals 1 of this original function, I have a horizontal tangent. Well, now I know that these are possible locations of relative extrema. Those are possible locations of maxes and mins. We will discover if they are maxes and mins and locations of those next class. This class, we're just going to worry about finding critical numbers. So do that for the next one. Every class. Stop. Check your answer with the neighbor. Yes.
You only have to worry about the function being undefined if there's a numerator and denominator.
Exactly. Exactly. If you get 0 and 8, we factor this guy. We know it'll never be undefined. Mr. Uso asked a great question. Will it be undefined only when we have a denominator? The answer is yes. If we have a derivative that has a denominator, we'll talk about what we have to do to figure out when that derivative is undefined. So we get 0 and 8. Now, let's not be confused in the future. If we ever just factor out a number, like we end up with 12 times x minus 1, x is 0 is not a solution to this. I plug in 0, I do not get 0. Okay, so make sure we know that it's only when we factor out a x that 0 is a possible solution. And again, these are possible locations of relative extrema. Yes, sir.
Why are they relative?
Well, we're going to have to do a lot more analysis to see if it's an absolute. Okay, all I know is that given a function that, say, has something like this, and this is at 0, and this is at 1. This is a horizontal tangent. This is a horizontal tangent. Boom, they're relative extrema. We'll see that. But neither are absolute extrema. So finding out if they're absolute extrema almost becomes really, really difficult unless we sometimes set an interval that we need to look in. If I say look between here and here, you would say, yeah, that's a relative and an absolute extrema. But we're not going to worry about it. We're just going to worry about if it's a relative extrema. Because some relative extremas, like this guy and this guy, this is a local max. They're also absolute maxes. Okay? So all absolute extremas are relative. All right, let's do this one real quick. Just as practice. Now, while you guys are using the product rule, I'm distributing and then taking the derivative. We'll get the same answers, but keep the process of simplifying in mind before you go crazy with any rule. It's very important to remember that in the future. That's a 2. Questions? These are all very similar to each other. We're all factoring out x's. Some of them, they won't be as simple. Some of them, we'd end up with, 3x squared minus 6x minus 9. We'd have to simplify a quadratic, but we would just factor like we know we can. So let's move on to something with a square root, or derivatives that have denominators. We have g of t is equal to t times root 4 minus t. I ask you to find the critical points of this function. That's finding when the derivative equals 0 or it's undefined. So let's find the derivative. Let's set it equal to 0 or see if it's undefined anywhere. So make sure we know this is a product. Go ahead and use the product rule. F prime g plus g prime don't forget to multiply by the derivative of the inside. The derivative of 4 minus t is -1 times t, which is f. All of our work we did last unit is helping us be successful for this unit. Because it's the derivative of the outside, leave the inside, times the derivative of the inside. The inside, 4 minus t, that's 4 times, or 4 plus -1t. The derivative of -1t is -1. Okay, so I'm going to first rewrite this. So I get rid of the negative exponent. should have a 2 down here. Now, before I set this equal to 0 or undefined, I can, but I kind of want things to be one fraction. I'll show you why after we make it one fraction. So whenever we have two separate terms, we need a common denominator to add them together. Just multiply our first term by 2 root 4 minus t to give it that common denominator. The top and the bottom. Too big. That would leave me with 2 times the quantity 4 minus t plus negative t all over my common denominator. Okay, pause here. Whenever I asked you to find a horizontal tangent and you ended up with a derivative that was a fraction, what did you have to do to solve this set equal to 0? Just worry about the numerator, right? So when I'm trying to figure out when f prime of x is equal to 0, I just have the numerator set equal to 0. But now I'm also wondering when my derivative is undefined. When do you think that occurs? When the denominator is equal to 0. So we need to set the numerator and the denominator both equal to 0 separately to find when I have a critical point, either a horizontal tangent or a undefined tangent. Will be for actual numbers as well. This on the left, the top would be 8 minus 3t, which is equal to 0. I'd get t would equal 3/8. Here, I can divide by 2. I can square. Essentially, it just becomes when is 4 minus t equal to 0. That's when t equals 4. Sorry, 8/3, not 3/8. Sorry. Okay, these are critical points, maybe. Whenever we have situations when we have a derivative that's undefined, we need to go back and check to make sure that it works in my original function and that those points are defined. So if I plug in 8/3, I get 8/3 times 4 minus 8/3 square rooted. That's fine. This one checks out. I plug in 4 into my original equation. I got 4 times the square root of 0. That's 0. That's fine too. If we ever have a situation with the square root of a negative value, that is where my function won't be defined and I can't necessarily have a critical value for my real values of my function. Okay? So if I ever have this, we won't have a critical value. What's up? Yeah, we're not going to deal with imaginary numbers. I'll show you how in the next example we'll see how we're actually going to be finding critical values of the imaginary graph of our solution, but we're not going to be graphing imaginary equations or imaginary functions at all. Okay, so those are my two critical values. Boom, they check out, they both work in my original function, we're good. Let's do another one with the square roots. Let's do this and throw an x in front of it. So find the critical values, and then check to make sure they work and that they are critical values. Is Miss Moore still outside with Mr. Musica? Oh my goodness. Sorry guys, it's been like 30 minutes. You'll have to catch up. Mr. Schlottiger can catch you up real fast. Okay, let's go do the problem. All we're seeing is where the derivative of this equals 0 or when it's undefined. That's it. Find the derivative, simplify a little bit, multiply the top and bottom to get a common denominator, set the top and the bottom equal to 0. This is stuff that you could have been asked to do last unit. I get plus or minus 2 and then plus or minus root 2. Just setting the derivatives equal to 0. Questions on how I got these? It all comes down to this, which is my fraction, which is my derivative set equal to 0, or seeing when it's undefined. Okay, that gives me 6x squared minus 12 is equal to 0. X is equal to plus or minus root 2. It comes from there. And then the denominator set equal to 0 would be this. Now, you square both sides, doesn't really change anything, okay? It's not going to be plus or minus 0. It would be plus or minus 0, but that's still 0. You get x squared is equal to 4. X is plus or minus 2. Now, are all these critical values for my real function?
No.
Which ones are not? Yeah, the root 2's, if we go back into our original function, if I plug in root 2 or negative root 2, I get 3 times 2, which is 6, minus 12. So I get the square roots of negative 6 both times. This is an imaginary number. So you would say that even though your instincts are telling you these are critical points, you would say these are not in your domain. So for the real function, you would say those are not critical. Now, if you go and actually look at the graph, this is the graph. Okay? The blue part is the real part. So only when x is bigger than 2 or equal to 2 will this function be defined. So past 2, 3, 4, 5, we see the blue part. And here's the blue part. But this orange part is the computer graphing the imaginary part. You can see that at root 2, we have what looks to be a local maximum. And at negative root 2, we have what looks to be a local minimum. So we actually are finding interesting parts of my function. It's just in this class, we don't necessarily care about those imaginary parts. Maybe in future classes you will, but not right now. I still want you to find them, but then analyze them.
So for our homework, we write like x equals plus minus 2, and we write x doesn't equal plus or minus root 2.
You just say not in domain.
So we write it down and say not in domain.
Yeah. Write down, say not in domain.
And that can be all roots or all just names.
Whenever you have something that's not defined for your original function, so the square root of a negative, or if you have a situation where you get a function that's 1 over x, guess what? When we set this derivative equal to 0, the derivative of this is negative 1 over x squared. This is undefined at x equals 0, so we think 0 is a critical value. Well, 0 is not defined in my original function. It's actually a location of a vertical asymptote. So you actually would not consider that a critical point because there's no point in general.
And so with the positive radical, like it has a positive square root 2, would you have to plug that back into the function?
Yes, you take both the plus and the minus root 2 and plug it back in and see if it works. And both of them don't work.
Okay.
Because they both give you negative values underneath the square root.
And we'll have to do that for all the radicals of the number?
All the radicals, all the fractions, like this guy. Find the critical values of this guy. Make this a minus in the bottom. And make this a 4 minus x up top. Just for fun. I don't know if that's going to change anything. Find the derivative, set it equal to 0. That's all we're doing. Nothing new. It's just a new way we're asking it. We are now asking this, find the critical points instead of find the horizontal tangents. We now know the locations of these critical points could be locations of relative maxes or mins. Did we really get that? Yeah? Okay. Pause there. Don't worry. Yeah, so we'll actually talk about, like, most of the problems that you'll be given will be set up so that you can take this and factor it, -7 and -1, you know, to get that. But in the future in this class, there will be some situations where you'll be given your calculator and you'll be given this and you'll be asked to find the critical points. So this is a good little pause, interlude, to figure out how to solve this quickly using your calculator. You'll never really be asked to use the quadratic formula. I don't think I've ever seen the quadratic formula be used in the class. Either you can factor it, or you'll have your calculator to solve it quickly. So get your calculators out. This will be a good little test to make sure you can find these answers quickly. How do you solve this using your calculator? Yeah, graph the left side, graph the right side, see where they intersect. That is the easiest way Thank you. Okay, so there might not even be a solution to this. Let's see. X squared. No, there'll be a solution. Minus 8x plus 1. I graph 0. I get 2 solutions. To find the solutions, go to trace and go to intersect. You can enter over 1, 0.127. I think it was positive. Positive. .871 is the second one. To find the second one, calculate, intersect. Pop over. You can even click on a value. I thought, maybe not. If you go on trace, yeah, go to trace, then go to the value 7. Then we could pop over to our intersection second, calc, intersect, enter, enter, enter. 7.87? Okay, so those are two critical points of my original function. I actually have 4, because when my denominator is set equal to 0, that's when my derivative is undefined. However, are these values considered critical points? What do you think, Ms. Wise? So -1 and the 1 that I found, are those critical points?
No, the negative one. No, they're not, because when you plug them back in, it's 0.
Exactly. Turns out if you plug them back in, you'll get 0 on the bottom of my original function. That means these are not in my domain. And turns out we just found a location of a vertical asymptote. Okay? Cool. So, that was interesting. We could do it for trig functions as well. It's set the derivative equal to 0. I'm just going to do the first one. Set this equal to 0. What should I do first? Yeah, you can divide by pi, and 0 divided by pi is just 0. Get rid of the pi. Now, let's remember how to solve this. We treat this as the cosine of some other value being equal to 0. So the cosine of y is equal to 0. You find your coordinates for y. That's pi over 2, 3 pi over 2, etc. Goes on forever. Then what do you do, Ms. Wheatley? Perfect. Go back, instead of y, make it pi t. And then what do we do, Mr. Brewer? Simplify how? Yes. Divide everything by pi. You get t is equal to 1/2, 3/2, etc., etc. Okay, we do the other one, but we got to move on. Rolle's theorem and the mean value theorem. I'm going to teach you the mean value theorem first, and I'll show you how the Rolle's theorem, you don't have to know it, because it's really the same as the mean value theorem. This is your second theorem of the 2 that you really need to know out of this class. The first theorem was the intermediate value theorem. Dealt with, being continuous and how you have to hit every single point between 2 points. Mean value theorem is kind of similar, only it deals with derivatives. Okay, so if f is differentiable, and f being differentiable means it must be continuous, because you can't be differentiable unless you're continuous. Given f of a and f of b, so maybe on a graph, put down an a, put down a b, put down f of a, put down f of b, the y value. There must exist some c value, or x value c, just so I don't confuse you, between the x values of a and b such that f prime of that c equals the slopes, or the slope between a and b. I'll say the slope between the points at a and b. Okay, you guys do me a favor, go ahead and connect A and B in any way that you see fit. Maybe you just kind of make a little hump or something like that. Maybe you do a straight line. Maybe you do a couple squigglies, whatever you want to do. Okay? I'm telling you that if you drew your function so that it is continuous and differentiable, meaning no sharp points, there is some c value somewhere that I can drag, and somewhere this c value will produce a derivative that's equal to the slope between this point A and B. So find the c on your graph. There might be one, there might be multiple. I just know there's at least one. For me, my c value looks to be right about here, because the derivative right here looks to be equal to that slope of that tangent, or slope of that secant. Yep, there could be more than one. There's at least one.
Should you label them like C1, C2, or?
Sure, or just, yeah. Here's one of my c's. Okay, another way to say this is that the derivative at c is equal to, instead of the slope between the points at a and b, you can use the slope formula. F of b minus f of a over a minus b, or b minus a. Now, this is not true if I draw my graph like this. If I have a sharp point, I cannot find a location where my tangent is going to be like that. These slopes are negative. These slopes are very, very positive. Maybe right here I see it, but maybe I can like make the graph even more crazy and just say straight line here, straight line here. This slope being consistent is not equal to this. This slope being consistent everywhere is not equal to that. Boom, the mean value theorem does not apply. So the key to the mean value theorem is your function has to be differentiable everywhere on this interval. So underline, highlight, do whatever you can to show that this is the key. If it's not differentiable, you might have a situation like this. You cannot confidently say that the mean value theorem holds. Now, let's go to roll. You're going to be able to answer this. Rolle's theorem starts as the same as the mean value theorem. F of x is differentiable. Given f of a equals f of b, there must exist a c between a and b such that f prime of c equals, you guys figure it out. Here's a, f of a, I'm saying f of b is the same. So f prime of c has to equal what? 0. Using the mean value theorem, you say, oh, it equals the slope between these 2 points. The slope between these 2 points is 0. Well, look at that. However I connect it, I will find that c that we're looking for. Okay, piece of cake, so long as we know the function is differentiable. Now we'll be asked to show that the mean value theorem or the Rolle's theorem, you can think about really mean value theorem strictly. You don't really care about Rolle's because you know that the mean value theorem almost shows Rolle's because it's the slope between the 2 points. We could show that it works on an interval for a specific function, and you'll be asked questions like this on your homework. Well, it's simple. Follow the definition. The derivative of your function must equal your slope between the points at -2 and 2. And these are the points from your original function. So I take f prime, which is 4x cubed minus 4x. I set it equal to the slope between the 2 points at -2 and 2. So that's f of 2 minus f of -2 over 2 minus -2. 2 to the 4th is 16 minus 2 squared is 4 times 2 is 8, so this is 8. I plug in -2, I get 8 as well. This is over 4. So to show that the mean value theorem or Rolle's theorem works, in this case, because the slope of these 2 points is 0, I just take my derivative, set it equal to 0, and find the points that I'm looking for in this interval. I factor. I then can solve. And all 3 of these points are considered those c values where the tangent slope at that c value is equal to the slope of the secant between -2 and 2. Okay, you guys do that with this one. Same question, you don't have to rewrite this statement. It's just show that the mean value theorem applies. Of course, you'd have to kind of think in your head, hey, this function is continuous. Hey, this function is differentiable everywhere. Once you've established that, okay, it is continuous, it is differentiable, then you can go about the process of seeing when the derivative is equal to the slope between those 2 points.
You don't have to write a long statement like you're in for the other thing.
The long statement can be written. You won't have to do it on your homework, but the long statement would be, since this function is differentiable between -2 and 1, there must exist a derivative between -2 and 1 such that the slope, or there must be a point C between -2 and 1 such that the slope at C is equal to the slope between -2 and 1, and I found it at that -0.5. So it's not the same as the intermediate value theorem in terms of the statement. It's a little bit different. Okay, your homework really quickly. We'll have questions on the odds that are dealing with absolute extrema. I don't want you to find absolute extrema. On the directions of your homework, I just want you to find the critical numbers. So don't worry about the odds and what they're doing for the odds. Just set your derivatives equal to 0 and practice finding the derivatives equal to 0 and undefined, okay? I'm going to do a couple more problems for the people who are watching this video on the B-Day. All right, let's do a couple more problems. Also, I want you to work using your calculator for a little bit, and then you'll be able to start your homework. These are the B-Day classes that I'm talking to right now, and any A-Dayers who miss class. So let's do this one. Let's determine if the mean value theorem can be applied, and if so, find all the values of C. Well, first I'm thinking sine. Sine is continuous everywhere. I know sine doesn't have any sharp points or any locations where we'd not be differentiable. So boom, mean value theorem applies. That's step one. Now we need to find the C. So I need to see when is f prime equal to the slope between pi and 0. So that's sine of pi minus sine of 0 over pi minus 0. And I'll go ahead and just find f prime. F prime is cosine. Sine of pi is 0. Sine of 0 is 0. So this is 0 over pi. So the question is, when is cosine equal to 0 between 0 and pi? Well, at pi over 2. So that's the C value that I'm looking for. To show that the mean value theorem works and that there is at least one value. Might as well do this one. So 4 minus 4 over x, show that the mean value theorem holds from the interval 1 to 4. Well, first I make sure that I know that I'm continuous and differentiable. This function would not be continuous at x equals 0. However, my interval is from 1 to 4, so I don't care that it's not continuous at 0 because it will be from 1 to 4. Next, let's just find the derivative, and we will set that equal to the slope. So that'd be 4 f of 4 minus f of 1 over 4 minus 1. F of 4, plugging in 4, I got 4 minus 4 over 4, that's 3. And plugging in 1, I get 4 minus 4, which is 0. And then in the bottom, I have 4 minus 1, so I get 3 over 3, that's 1. Easy. So now I take the derivative. So this becomes negative 4 over x. I can rewrite this as negative 4x to the negative first. So the derivative would be positive 4 x to the negative second, or 4 over x squared. I'm seeing when that equals 1, not x. Multiply both sides by x squared. Solve for x, we get plus or minus 2. The value that we're looking for is between the interval of 1 and 4. So plus and minus 2 are values when the slope of the tangent is 1. However, the value that we would say satisfies the mean value theorem would just be the 2. being between the 1 and the 4. Okay? Similar problem here, same process. Now, one thing I want you to know is that using a calculator is going to be a great way for us to be able to check the critical points that we're finding. And also on the AP test, on calculator portions, and we'll practice this before we take AP tests or a midterm, which is a practice AP test, you'll be asked to use your calculator to find critical points. So example would be like this. Find the critical points. Well, if I didn't have my calculator, I would try to have to factor this to solve. And maybe it's not as bad as I thought, but it isn't. It's bad, okay? I need to set this equal to 0, and that's really tough. But if I have a calculator, it's not tough. We graph the left side, we graph the right side, we see where they intersect, just like I did earlier. So let's go ahead and find these critical values, if there is any. There might not be any. So I have 4x to the 4th minus 12x cubed plus 2, that's my derivative, and I set that equal to 0, and I can graph and see if I have any intersections. I got 2, it looks like. Second, calculate intersects. You can find your first one, your second guy, and solve. Gets me 1 at 0.592. On the AP test, you will be asked to simplify to, I believe, 3 decimal places. It might be 4. Doesn't matter if you truncate it or if you round it at the end. We'll talk about that more as we get closer. And then the second one, I could do a second calc intersect. Go ahead and scroll over to the second intersection right here. Enter, enter, enter. Looks like it's an easy value, but it's not. It's at 2.9811. Okay? So for something like this, you have to use your calculator. Now, you can use your calculator to help you check your answers that you're doing by hand, especially the ones with these square roots that we're setting equal to 0, okay? Now, a typical problem would be the following. Let me type this up. How many critical points are there to that function, or I guess 4, on the interval between 0 and 1. Okay? This is first testing you to make sure you know how to find your derivative of this, and then it's going to be testing your calculator knowledge and your ability to change up an interval to find the amount of critical points. So to find the critical points, we'll set this derivative equal to 0, or we'll see where it's undefined. So we have to use the chain rule to take this derivative. Of course, we know we can write this as cosine of 3x squared minus 2 quantity squared. So I'd take the derivative of the outside, leave the inside, times the derivative of my next piece, times the derivative of my last piece. So this is 2 times cosine 3x squared minus 2 minus sine of 3x squared minus 2 times 6x. Now, I need to find the critical point, so I'll set that equal to 0. Well, I can't solve this by hand, and if you can, let me know how you do it, because it's just not able to be done. We need a calculator to help us with this. So, graph the equation, set it equal to 0, and let's see what happens. 2 cosine 3x squared minus 2, close the parentheses, times negative sine of 3x squared minus 2, close the parentheses, times 6x. and I see we have a whole boatload of solutions. Because it's cosine and sine. It's oscillating. It's being multiplied by 6x too. So it's, of course, growing while we're oscillating. And then I get over here, and it's like I can't see what's going on in here. So a question like this on the AP exam, you would need to know how to adjust your window so that you're only looking on the interval that you're really caring about, which is between 0 and 1. And you can even adjust your y min and your y max so that when you graph, we only are looking from 0 to 1, and we're looking from -2 to 2. So I can see I have 1, 2 solutions between 0 and 2. And I think 0 is also 1. I'd probably include 0 as well. So maybe if I zoom and window to like -0.5, we can see that at 0. There's my first one at 0. I have 1. There's 2 critical points. And here's a third critical point. So you'd answer 3. And that would be a typical question asked of you on an AP exam that you would have to do on your calculator. So use your calculator to help you find critical points. You can also use it when you're trying to find the mean value theorem being true. This is a good example. So the derivative is 6x. Well, let's make this cubed. Make it a little tough. Make this 8x. Sure. So the derivative would be 9x squared minus 8. And I'm seeing when that equals the slope between these 2 points. So that's 8 times 3, that's 24, minus 16 is 8. And then I got 3 minus 8, that's -5. So, well, it's not the worst. But it can be done with a calculator. You get 9x squared minus 8 is equal to 3. 24. Yep. Well, if I wanted to solve this by hand, I could. I just have to take the square root. But if I wanted to double check, I can set the left side equal to the right side by graphing. And I can even plug in 3. No big deal. Go back to Zoom Standard. I'll see I'll have 2 solutions right here and right here. One will be the opposite of the other. .1055, which is the square root of something. Okay, so just different examples of using your calculator to help you find some answers. Go ahead and use your calculator on your homework to check your answers, but of course on your quiz you're not going to be able to use your calculator to find these critical values. And just a reminder on the homework, don't find the absolute maxes and mins. We're not worrying about that until a future unit. We're just finding critical points. Next class, we will then analyze if these critical points are the locations of maxes or mins. It's going to be great. All right. Have a good day. Have a good weekend. See you guys next class.